Hello everyone, good morning, good afternoon, good evening, and welcome to another Sophion hosted webinar today. I think as typical, we typically allow a little bit of time for everyone to join, to not start exactly on time, but I think we have a very exciting program for you today. And whilst we're waiting, maybe just like 2 minutes, 3 minutes or so, I'm going to play a little clip for you introducing the QPatch Compact platform, which is the technology that this webinar is going to center around today.
QPatch Compact is a semi-automated patch clamp system that makes patch clamping accessible to anyone. You do the pipetting. QPatch Compact does the rest. With QPatch Compact, you can conduct up to 8 experiments at the same time. Each experiment can be independent to investigate biophysical parameters, or they can be replicas to increase the statistical power of your experiments. In the Q plate, where the cells are sealed and formed into whole cells, microfluidic flow channels and glass surfaces ensure good liquid handling. It is easy and ready to use when you are. Everything is explained on the screen and recorded for your documentation when making the analysis. Avoid the hassle and complexity of manual patch clamp setups. With QPatch Compact, you can focus on generating data. No hassle, just data. The data are stored on a separate hard drive inside the instrument, and there is automatically backup. You can analyze the data from anywhere without any extra software, and it is also possible to export it. You can place it where you want, though it is still so stable that you don't need to fear that anybody bumps into it and destroys your experiments. When you receive it, all you have to do is plug it in and turn it on. If you are interested in learning more about QPatch Compact, please check our website, sophion.com, or send an email to info@sophion.com.
All right, welcome again. Good morning, good afternoon, good evening to this Sophion hosted webinar. And yeah, it's thank you for joining us for this session today. I'm getting a text that there might be a problem with the sound, but the test earlier sounded like it worked out fine. So today we have another very exciting meeting for you where we have a bit of a different content. So using Sophion's technology to support graduate or undergraduate education is not a new thing as such. We have done this for quite some time that dates back. We have given several undergraduate course presentations in the UK, but also in Mexico or in the US and in Europe, where we support sort of the training of the next generation of electrophysiologists. But aside from providing seminar presentations, we've also participated in various courses, practical courses. And today, I have the pleasure of sharing an example that we've recently done with our newly or relatively newly released semi-automated patch clamp system, the QPatch Compact, where we had the chance to support the renowned neuroscience graduate program at Brown University that is led by Professor Diane Lipscombe. And I think it's a particular pleasure to me that today we will receive feedback from Diane Lipscombe herself and 2 of her first-year graduate students that will present about their experience with using this technology in a training setting. But before we go into this, I have a few housekeeping items that I would like to touch upon. And that is, if you do have questions during the various presentations, please keep them coming. We'd always like to hear from you. You can post your questions in the chat, and we will then, after all the presentations are completed, we will then go one by one through all the questions and answer them, or the various presenters will then address the various questions. We are recording this webinar, and at the end of the webinar, you will receive an email containing a link where you then can download or watch this webinar again, or just share with colleagues who might be interested in this topic. Also, you will see here on this right-hand section where you see the chat, you will also a section that's called handouts. And here we have uploaded our QPatch Compact brochure where you can get more information about the platform. But obviously, that's not limited there. If you do have more questions about it, you can look at our webpage where we have a much more detailed section about the QPatch Compact with videos, introducing videos like the one I've showed just now, introducing some of the work with that technology. But then importantly, the entire Sophion team is, of course, always there for you in case you do want to learn more about it, or in case you have a graduate or undergraduate course that you would feel where automated patch clamp is well suited to come and be introduced, then we'd be eager to hear about this. So before we now go to the main topic of the presentation, I have the pleasure of introducing our Global Product Manager for the QPatch Compact system, Michael Sonnestel. Michael will introduce the QPatch Compact and Sophion in a bit more detail before we are starting into the use of this technology in a educational setting. So a few words about Michael. Michael has been with Sophion since the beginning of 2022, where he has overtaken the role as the global product manager for this technology, and really has been listening to the needs of the market to further refine and optimize this technology so it really can benefit all the various applications that you have with this technology. So without further ado, Michael, the stage is yours. I'm just going to pull up your presentation here. And all right, the stage is yours.
Thank you. Thank you very much, Daniel. Hi, I'm Michael Sonnested. I represent Sophion Bioscience, which is a global biotech company based in Copenhagen, Denmark, specializing in automated patch clamp. We're working with academia, CROs, cell line providers, and pharma companies in developing ion channel assays. This way, we assist in developing better and safer drugs and have been doing this for the past 20 years plus. While we are mostly known for medium to high throughput automated patch clamp instruments, we decided to develop a new product called QPatch Compact. This was especially aimed at the academic market, as we had seen increasing interest in APC, automated patch clamp, but often challenged by justifying the investment. We also experienced a demand for more flexibility during experiments, which was not available with existing APC instruments. And electrophysiology researchers who did not do patch clamp would sometimes need to supplement their research with patch clamp data, and accessing this kind of data would often be challenging. The main objectives for releasing this new instrument was to enable high-quality patch clamp recordings based on our proven technology, while keeping the instrument small, mobile, and easy to set up and operate. We wanted to enable multi-user mode and offer a fully integrated and practically maintenance-free system. In fact, it turned out to be as easy to operate that only minimal training was required. If you can pipette, you can patch clamp, we like to say, and it sets up in just 10 minutes. It is self-calibrated, and you can generate patch clamp data in just a few hours of starting to use it. So as Daniel also mentioned, QPatch Compact has been used at several universities for teaching grad students, among which is Brown University based in Rhode Island. I myself had the great pleasure of visiting during the neuroscience course held by Brown University and led by Diane Lipscombe at the Marine Biological Lab in Woods Hole, earlier this year. And it was extremely exciting to firsthand witness how the students and faculty members were able to efficiently characterize ion channels by running experiments on QPatch Compact to evaluate the outcome and reiterate experimental conditions with an incredibly short turnaround time. You will hear much more about their experience from the neuroscience course in just a minute.
All right. Thank you very much, Michael. I actually don't know if your slides moved now. All right. Well, thank you, Michael. But I think before we, if you do have questions about the technology, please post them in the chat and keep those questions coming. We're then going to answer them at the end of the presentation. So now I have the pleasure of introducing our next speaker, and we're moving to the main topic of the presentation today. So our next speaker really doesn't require so much of an introduction, but I would still like to use some of the time, a few words to introduce our Professor Diane Lipscombe. So Diane Lipscombe is the Reliance Dhirubhai Ambani Director of the Robert J. and Nancy D. Carney Institute for Brain Science and Thomas J. Watson Jr. Professor of Science in the Department of Neuroscience at Brown University. So Diane really is a leading figure in the ion channel research field, and she has contributed significantly to, for example, the understanding of neuronal voltage-gated calcium channels in various health and disease states, including chronic pain. So her lab discovered new mechanisms that control cell-specific pre-mRNA splicing of voltage-gated calcium channels, important for the control of synaptic transmission and regulating the sensitivity of nociceptors to heat. Also importantly, Diane Lipscombe is the past president of the Society for Neuroscience, a member of the American Academy of Arts and Science, and an honorary fellow of the Physiological Society. Also importantly, she is the recipient of several awards for teaching and mentorship. And Professor Lipscombe has a history of working to improve and enhance graduate education and training. And particularly because of this, we are very interested in hearing the feedback from Diane of working with the QPatch Compact technology in a teaching setting. So Diane is going to provide an overview of the use of this technology to introduce whole cell currents and basic biophysical studies of ion channels. And she's then followed by two of her first-year graduate students, Adit Sabnis, who is a first-year student in the neuroscience graduate program. And Adit will present a bit about the data acquisition portion. And then we have Alice Lin, who is currently an MD, PhD student, finishing her first year at Brown University. And Alice will introduce some analysis that she had developed during the course, where you can showing how you can work with the data produced by the QPatch Compact. So without further ado, Diane, please, the stage is yours. And if you wouldn't mind clicking the slides, I think that may have been a misunderstanding in the previous presentation.
Great. Yeah, thanks very much. Just wanted to make sure everyone can hear me. So Diane Lipscombe, I got a great introduction there. Thank you very much. But as was said, I'm a professor of neuroscience at Brown. I actually run the electrophysiology section of a course that I'm going to talk to you about that was already previously mentioned. And then, as Daniel said, then Adit and Alice will join us to talk about their experience. So this is the overview that I have planned, and I'll just talk for about 10 minutes. But for context, I just wanted to mention, you know, the course that I'm involved in. It's a first-year neuroscience graduate student kind of methods in neuroscience course. Electrophysiology is one piece of the course. And it follows a semester-long kind of didactic lectures that the first-year graduate students, all take. And in particular, what's relevant to electrophysiology methodology is the cell molecular neurobiology course. So the methods focused course is kind of an 8-day immersive hands-on research experience, and we hold that off-site at the Marine Biology Labs in Woods Hole in the United States. We're there in mid-January, which is very cold, windy, and so that just keeps us in the lab, and it's just a really great experience to have this very immersive opportunity for the students to see in real life the things that they've been learning in class. There's about 12 to 16 students, and those students are broken up into groups of 3 to 4, depending on the size of the class in any given year. And then they each do 2-day rotations on 4 different experimental setups. And as was already mentioned, I run the electrophysiology section. The other thing to mention is that the graduate students have very different backgrounds, and some, well, I mean, pretty much everybody has had lab experience, but many actually have never seen a patch clamp setup, let alone actually had hands-on experience with that. So they come in with the basic knowledge, the classroom course, but no hands-on experience. The other rigs, just for completion, in addition to electrophysiology, we have a C. elegans experimental setup, do experimental design, data acquisition analysis, and also typically there's an imaging setup as well. So that's the course background. The objectives that we have going into the electrophysiology section is a number of objectives, but basically, you know, what's the basic principles underlying the ionic basis of excitability, and of course, with a focus on ion channels. I work on voltage-gated calcium ion channels, and so we tend to use those, but I like to indicate to the students how pharmacologically, but also electrophysiologically, one can isolate the ion channel currents with a focus on voltage-gated currents. And then to show them through different experimental protocols, the elementary factors that influence current flow. So the number of channels, the channel open probability, and how much current flows through a single channel, for example. And then apply the voltage clamp methodology to demonstrate, for example, how current flow through the channels depends on membrane voltage, to introduce the time dependencies of current flow as a function of voltage, and to third, to show the value of recording tail currents. And for those of you who do a lot of voltage clamp, then this will make sense to you, but I've got a couple of slides to indicate why we focus on tail currents. But that allows us to extract the voltage dependence of channel open probability and instantaneous current voltage relationships. And then in addition, to look at the voltage dependence of ion channeling activation. Of course, there's a much longer list, but these are the things that I absolutely touch on every year in the electrophysiology section of the course. And Adi and Alice will talk about some of those protocols that they were able to develop on the fly. And Alice has data to show you as well. So typically we're using the manual wholesale patch clamp setup, which I learned as a graduate student too many years ago. But I think most of you are familiar with the power of this methodology, tremendous. But of course, in manual patching, you're using individual electrodes to patch, for example, individual cells. So in a teaching setting, we like to show the students how to start at the beginning and work through the flow and all of the logistics that are needed to set up the wholesale patch clamp. But of course, that means manufacturing pipettes, filling the pipettes, loading the pipettes, finding the pipettes in the microscope, and very often breaking them. And then if one can get the tip of the pipette onto the surface of the cell, then forming a gigaseal and then breaking through to form a wholesale recording if one is doing wholesale recording. And of course, what really matters in a teaching setting and in every setting is, how stable is the recording, and that's going to determine the length of the recording that one is going to be able to achieve. I'm going to just run through. These are actually currents that we recorded in my lab, but it gives you this is through manual patching, but Alice will show you the data that that the students got using the automated patch setup. But I'm just going to kind of run through a couple of the protocols so that then Adi and Alice's presentations will be placed in the right context. So I mentioned our focus on voltage-gated ion channels, and these happen to be voltage-gated calcium currents, as I said, measured in my lab through manual whole cell patch recording. These are cloned calcium channel currents expressed in a human embryonic kidney cell line. But this is a standard test protocol going from -60 to +80 millivolts. So you can see the currents are activating as the membrane voltage test potential is increased. And this generates, if you measure the peak current and plot the peak current against test voltage, you can see this very beautiful and classic kind of U-shaped current voltage relationship, which is absolutely classic for voltage-gated calcium, but also voltage-gated sodium currents. And at any moment in time, the calcium current is going to be a function of the single channel current amplitude, the number of channels that are present and available to be opened, and the channel open probability. So this would be the calcium, the current voltage relationship. One is able to then use a number of different protocols, and here's one example to extract, for example, the relationship of channel open probability, the activation curve based on test voltage. And that can be done using the tail current. Again, Alice is going to show you some examples of that, and just thought I would go through it very quickly. But here we're varying the pre-pulse potential, similar to what I showed you before. But rather than measure the current that's generated during this pre-pulse, we're measuring the current, the tail current that you can see here at a fixed voltage at -60 millivolts. And so you can see the tail current, the tail currents here are plotted here, and that allows us to extract the channel open probability according to the pre-pulse potential here. So that's what's plotted here. And so the idea is that with different pre-pulses, the channel is opening more and more and more as the membrane voltage is being more and more depolarized. There are two things that are working in concert during the test, during the pre-pulse. Let me just go back a second. During this pre-pulse, you can see the current gets bigger and bigger, but the peak current starts to get smaller and smaller. And that's because channel open probability is increasing, but the driving force is decreasing. So if one just looks at the tail potential at a given value, you can measure the current just at the point before the channels start to close, and the peak of the tail current gives you a really beautiful measure of the channel open probability at these different pre-pulse potentials. And the key thing here is that the tail currents are measured at exactly the same voltage, so the driving force is the same all the way through. Again, these are the protocols that we develop in the lab as I'm teaching the students about the properties, the voltage dependence of channel gating, and the different components that are contributing to the total current. This is another protocol that Alice, I think, may show you, but we certainly did this in the course, varying the pre-pulse just as I showed before, but then doing a test pulse and then measuring how much current is available at the same test pulse with these pre-pulses occurring before the test pulse. So now we're measuring the peak current here during this test pulse to 0 millivolts. And as we give more and more and more pre-pulses here, we can absorb the channels into the inactive state and generate this inactivation curve and plot the inactivation against the activation. And essentially, just to kind of ground you in why we would do these different protocols and how they're informing us about the properties of channels, we're essentially kind of probing some of these states that we know that voltage-gated ion channels can exist. And here's just a depiction up here showing that there are multiple closed states that voltage-gated ion channels exist in. And here's the open state. So this is the only open state, but the channels can also inactivate, and there are multiple inactivation states. So in probing the properties with the students of voltage-gated calcium channels, we're also able to demonstrate that the voltage-gated ion channels, and in this case, voltage-gated calcium channels, exist in discrete conformational states that contribute to our understanding of the ionic basis of excitability. So now, to giving that little bit of background, I'm just going to wrap up to talk a little bit about our experiences using manual versus automated, the QPatch Compact setup. And I would say that it was great, having spent many years doing manual patch setups with the students. Most of the time that we spend in the manual operation, just in this two-day rotation, was going through the mechanics of setting up the patch clamp rig. But as an instructor, what I think is the most valuable thing is to really start to dig into the data and show the students, allow students to be able to visualize currents in real time, and then on the fly to be able to modify their protocols to test various hypotheses. And so the focus is much more on the data and the analysis rather on the mechanics that require kind of dexterity and practice to be able to set up the patch clamp system. And so just running through these features, I just wanted to kind of reiterate these and then close and hand off to the students. But in my experience, the use of the automated patch for teaching in this kind of two-day block of time that I have with each of the sets of students, it really allowed me to be able to maximize time and focus on fundamental concepts. It really minimized time on the mechanics of setting up the experimental rig, so pulling the pipettes, less breaking pipettes, there's no pipettes involved. And then the seal formation is obviously automatic in the QPatch Compact. And that was actually very consistent. And so I was actually pretty pleased with that. It gave me a lot more time to do real-time teaching. We were able to modify the protocols on the fly, and you'll see some examples of that. And we were able to get a very large number of recordings over the two-day period of the course with each group of students. So every group of students was able to get recordings. And then they actually took some of those recordings in a course that happened in the following semester at Brown to focus on kind of coding, data acquisition, and analysis of the data that they were able to acquire. So that's my quick presentation, and I hope that was helpful to give some context in terms of the use of the QPatch Compact. But probably much more interesting will be the presentations by the students, and they're going to give you some perspective of what it was like for them to come out of the class and then go into this kind of real life experience doing patching for both of them, I think, for the first time, but they'll tell you about that. So I'm just going to now introduce Adit Sabnis, and as was already mentioned, Adit was a student. It doesn't seem that long ago now, thinking about it, but it was back in January. And so Adit, it's over to you to talk a little bit about your experience.
Sure, thanks, Diane. Hi, everyone. My name is Adit Sabnis. I'm a PhD student in Brown's neuroscience graduate program. Currently, my work is looking at electrophysiology in non-human primates, but my former lab, I did a lot of immuno and actually a lot of manual patch as well. So I'm going to be talking a bit about my experience working with QPatch, having formerly done manual patch. So I just wanted to give a little brief historical context for where QPatch fits into the electrophysiology landscape. So in the 1790s, Luigi Galvani was the first to show how electrical impulses could cause muscles to twitch in frog legs. Hodgkin and Huxley came around in the 1950s, and they were able to study or show the presence of the action potential in a giant squid neuron. But back then, they were still using electrical or metallic probes. And then in the 1980s, Nair and Sackman were able to come up with the technique known as patch clamp, which has sort of become one of the gold standards. So with that, having done manual patch clamp, Diane talked about this a little bit, but one of the most difficult things about doing patch clamp is the learning curve. It takes months of training oftentimes and hours on practice. And then an underrated feature is it requires proficiency with a lot of what can be complicated equipment. And then moving from rig to rig or having to do patch on one rig and then moving to a different rig can pose challenges as well. But with QPatch, really, when we were doing it, the only technical skill in terms of experimentation that we had to know was using a micropipette. And once we were able to micropipette the solutions in, all of the other sort of things from a learning standpoint were not very present. And because of that, it meant we were able to jump in to get data really quickly. With acquiring data, so one of the things is is the efficiency to acquire the data. So with manual patch clamp, you're typically only patching one cell at a time, and it can take a whole day to get multiple cells. Very common in my previous lab for people to say, "Oh, today was a good day. I got 4 or 5 cells." And then if you need to change your experimental conditions while recording, that's also a whole process as well because it requires changing the solutions you're using. Oftentimes you might have to transfer your stuff to a different day to allow your changes to take place. But with QPatch, you can do 8 cells at once. And what I think is one of the coolest things is you can adjust the experimental conditions between the wells and between trials without having to go through a really lengthy setup process to do that. And the last thing I'll say before I go into some visualizations of what we did, one of the big extra considerations when you're doing manual patch clamp is being cognizant of excess noise and vibrations and stability. Even something such as bumping the table that the rig is on can cause artifacts to be present in the data. But because QPatch was self-contained, we could focus a lot more on actually designing the experiments and getting the data rather than worrying about extraneous things that might have been present with manual patch. So as an example, with manual patch clamp, let's say you wanted to go through a few different cells, you wanted to change some of the voltage parameters or some of the time parameters. Typically what you do is you go in and you do those one by one. And then if you needed to change something, it would depend on how big the change is, whether or not you'd be able to change it, reset up your experiments, and then, or do it on another day. With QPatch, however, because there's 8 wells and because it's all automated, we could actually set up in advance exactly how we wanted our experiments to be run, exactly how we wanted each well to be run, what parameters we wanted each well to use, and what we wanted on each trial. And then the other thing that's really, really helpful, especially with respect to acquiring data on the fly, is the fact that you can modify it much easier than you can in manual patch clamp. So let's say you set up your entire protocol, and you're realizing, oh, we should have changed this. You can very easily go in and modify your protocols for the next few rounds so that you're able to collect exactly the data you want and really change it on the fly, like Diane said. And Alice will show some really, really beautiful analysis of some of the data we collected using these methods. So I'll just end on some of the differences. So manual patch clamp, you can patch through multi-layered neural tissue. So I used to work in the retina. So you could very easily go through multi-layers and find your specific cells. And you can use it to study cell-cell interactions as well as circuits. But for QPatch, it's better for monolayered cells. And so because of that, it's more useful to study the activity of individual channels and the properties of those channels rather than looking at circuits. But it serves a really great purpose. And I think next Alice will show us some of the actual data that we collected using all these things on the fly. And so, yeah, I'll hand it over to you, Alice.
Okay. Hello, everybody. My name's Alice. I'm a rising second-year graduate student at Brown University in the neuroscience department.
Alice,
Currently,
you might
I work
be
in a
muted, I think.
Oh, hello. Hello, can you hear me?
I did hear you just before, so I think it probably was fine. I also see some text coming through that the mic was on.
Okay, I guess the mic is on. But yes, hello everybody, my name is Alice. I'm a rising second year graduate student here at Brown University in the neuroscience department, and currently I work in a lab where we do a lot of electrophysiology. So I have some experience with the data analysis and data acquisition process required of electrophysiology. Like Diane and Audit have said, at the beginning of 2023, the first year neuroscience students had an opportunity to go to a special training camp hosted by Diane and a couple other faculty members, where we were able to learn about a lot of different techniques. And I'll be talking a little bit about what it was like gathering data there and what it was like to be doing data analysis afterwards. Okay, so first I'll talk a little bit about traditional patch clamp softwares that most electrophysiologists are accustomed to. So most softwares for patch clamp that are currently used are developed by molecular devices, and they have a software suite called the P-Clamp suite, where you would use Clamp X here on this left-hand side for data acquisition. It'll sync with the hardware you have to run the protocols that you need, and you would generally use Clamp Fit, the software in the middle, for analysis afterwards or during. So there are a couple requirements of using this particular device setup. First of all, when you're using ClampX and when you're trying to do electrophysiology, you really need to have compatible hardware. So for example, there are very specific requirements of both the digitizer and the amplifier. If it's not compatible with your system, then you're not going to be able to acquire data appropriately. Additionally, it requires a Windows computer. So I'm a Mac user, and this means I can't run any of these P-Clamp softwares on my Mac. And additionally, there's a 2 gigahertz processor minimum, which means if you have like a much older version of a Windows computer, you're not able to run these softwares, or it's going to be really slow and you're not going to be able to acquire or analyze on like a Chrome pad, like a tablet that you have on the side as someone else is running experiments. And finally, you need a lot of familiarity with these software. So there are a lot of buttons, and oftentimes like it takes maybe a week or two to learn what each button does, to not click the wrong button and accidentally kill yourselves, and how to open certain softwares when you want to do analysis, as opposed to the softwares you would open for running a particular protocol. And all the like exported data files are in the Axon binary format, so ABF. And these are pretty large files that you would not be able to open unless you're using P-Clamp, like any one of their software suite softwares, or if you're writing your homegrown code. So now that I've talked a little bit about the traditional patch clamp programs and how it's generally used, I'll talk a little bit about how it was for us to be like gathering data at Neuropracticum and how we were able to quickly analyze that data. So the data files that are exported, the like exported files from the QPatch Compact system are Excel files. So as you can see on this left-hand side, it's the time, and this time is in milliseconds. This entire first column is time. In the second column, it's the voltage. So it has the voltage like test pulse like settings that we put in. So basically our experimental design. And then this third column would be our like the data we collected. It represents the current. So this is an Excel file. Most of us have used Excel files just like in our day-to-day. So it's very accessible to the average student, and people have Excel on their Chrome, on their tablets. They have Excel on their Windows computers. They have it on their Mac. So it's very easy to use. And because Excel is such a straightforward software for a lot of people to use, a lot of us have familiarity with it, you can directly take Excel files and start plotting things. So for example, here on this like upper graph, I've plotted exactly what the voltage, like the design of the experiment, the voltage like the voltage column against the time column. So time on the x-axis and voltage on the y-axis. And you're able to see exactly the protocol that we ran. And here below, I've plotted the current on the y-axis and time on the x-axis. So I just plotted this third column against the time column. And we were able to see all these things. These are the same graphs that we were able to see actually on the QPatch Compact screen as we were running the protocols themselves. and they're the same protocol, and these are the same, this is the same data file that we're able to directly use without any further manipulation of data. We don't need to start writing code. We don't need to run it through a software. We just open Excel and directly just plot single sweep by single sweep. So this is how it looks like, what it looks like in Excel. So we wanted to run slightly more sophisticated analysis because we were able to generate so much data in such a short period of time. So while we were at Neuropracticum, that same first day when we started using the machine, that night, Audit and I wrote up some code in MATLAB because it's a coding language that's pretty familiar to the both of us. And we wanted to be able to iterate through the 15 different Excel files that were generated from that day of recording, which is a very, very, very large sample file, a very large amount of data compared to how much data you'd be able to normally get in a single day of electrophysiology. So this MATLAB code is really homegrown. It's accessible to people who maybe have a little bit of a coding background and maybe want to do much more high throughput analysis than simply graphing each individual sweep in Excel. So writing this code maybe took us 30 minutes at most. So it's very accessible to first year graduate students who have maybe some computational background, but not much of but slightly less of a electrophysiology background. So it was really straightforward for us to write this. And from this code that we wrote, we were able to already plot all the data. So this is the experimental design for a single test pulse to generate a current voltage curve. So here we have voltage on the y-axis and time on the x-axis, and you can see each of these colors represents a different sweep. So each time we increase the voltage of the test pulse. So we would start at low and then subsequently increase the voltage that we're injecting at that part. We're increasing the voltage at each individual point. And this is the data that we gather from that. So the colors all correspond, and you're able to see the current that we're generating via that same voltage test pulse. So current is on the y-axis, time is on the x-axis. And then we also ran separate experiments, for example, a 2-pulse protocol where we ran voltage test pulses and then brought it to a different voltage prior to bringing it back to baseline. And again, voltage on the y-axis and time on the x-axis. And we're able to, again, generate a lot of data and visualize it all in a way where Diane was able to lecture to us in the morning, where she was able to describe, okay, this is the type of curve that we would expect from, say, a sodium channel or a calcium channel. And subsequently later in the evening, we're able to plot all of this and visualize it all in accordance to the experiments that we had run. So now that I've talked a little bit about the same day analysis we were able to do using MATLAB, I'll talk a little bit about the long-term analysis that I did over the past semester. So as Diane said, we had a statistics class over this past semester where we were learning how to code in Python and learning how to do a lot more large-scale data manipulation. So this was code that I wrote over the course of maybe 2 or 3 weeks. And from that, for that project, for that class, I was able to look at all the data that we had acquired across Neuropracticum. So from data from multiple other groups where I was not present for their experimental acquisition. I have no idea what protocol they ran, and I just took the data that they generated and started running analysis on that. And for example, this code took a little bit to write, but it was pretty straightforward. Here's some data that I was able to process. So for example, again, up here, we have the voltage on the y-axis and time on the x-axis. This is the exact experiment that we had run, the running test pulses of voltage. And here's the current curves. We're able to visualize the current over time. And we're able to visualize it across every individual sweep that we ran. And from there, I took the maximal current change down here, the big slope, and I was able to map out the IV curve, the current voltage curve, where voltage is on the x-axis and current is on the y-axis. And we're able to see how, at different voltage, at different memory potentials, we're able to, the channel or this cell that is expressing a single type of channel will open or close certain, a certain number of this channels. And from there, We then, as Diane mentioned, examine specifically the tail current, this little section right here, which corresponds to exactly when we end the voltage test pulse and return the cell to baseline. So over in this specific area, I'm looking at how the current changes, and using that, I'm able to map I specifically take the maximal current change and then like scale each one of the currents, like for each individual sweep, to that maximal current change, and see how that specific current change maybe is greater than or less than the previous current change by XYZ amount. And subsequently, using Python, I'm able to run like curve fitting equations, and see what is the line of best fit, how can I best explain my data, how can I perhaps see what constants represent the equation that shows the number of available channels that changes over time or changes with the voltage changes. So for example, here on the x-axis I have voltage, on the y-axis I have the percentage of available channels, with 100% being at the top, 0% being at the bottom. And we see that as we increase the voltage of the test, as we increase the test pulse to say negative 40 millivolts or negative 35 millivolts, there are no channels that are available available to open in this tail current. And finally, we also studied, for example, one of the experiments that Audit had designed was to vary the time between two different voltage test pulses to see how long it would take for a single cell to for the channels in a single cell to recover. So here in yellow, that's the first pulse, and then each subsequent little line represents the exact point in time where we subsequently ran a second test pulse. And so here's a corresponding current plot to show exactly what that looks like. So here you have a very big response to this very first test pulse, and then each subsequent color represents a subsequent the second voltage injection in a separate sweep. So you can see this first yellow one, you really don't have a response. Subsequently, in this blue one, which corresponds to this exact time point when we're starting to inject the second test pulse, you see a response. And you can see that over time, as you increase the time with recovery, you see like a greater response in terms of in response to a test pulse. And from here, this plot really shows just like the percentage of recovered current versus the recovery time. So on the x-axis, as we increase recovery time, we see that there's an increase in percentage of recovered current. All right. And again, this line is fitted to just mapping the percentage, like comparing to the maximal change, and just mapping each one of these, just taking a percent, mapping out the percentage, and using curve fitting softwares to figure out, okay, like what would be the best way to just explain this equation. All right, and just a final slide, just explaining the benefits of QPatch Compact for data analysis. One, it's a really easily manipulatable data format, specifically those Excel files. It doesn't require any sort of programming background. It makes it really accessible to students who don't have a computational background. And it's really great for teaching because then you could just easily on the side, as someone else is doing recordings, you can just have somebody else sitting on an Excel file and just looking at what the previous data looked like. And two, it's accessible in multiple programming languages. Specifically, in our case, we tried both MATLAB and Python. It was great for us. And with the sheer amount of data that we gathered, it made it so we could do analysis in both MATLAB and Python and look for and find greater statistical significance in the experiments we ran. And I'll hand it back to Diane. Thank you.
All right. Well, thank you, everyone, very much. Thank you, Diane. Thank you, Adit, and thank you, Alice, for these very great presentations and for providing your feedback about your experience working with that technology. I think what is really getting clear to me, or what we hear also more and more from our clients, is that with the semi-automatic or the automatic patch clamp technology, we are moving away from a data acquisition problem more towards a data informatics problem. So I think for me, it was very insightful as well to see an approach where how you can sort of work with the data. I mean, many of our clients rely on the software that we have sort of matured over the past 2 decades and more. But I think it is very interesting to me as well to see that you can easily export the data and then use some advanced analysis methods to really extract exactly the data that you want. So we do have some questions available that I would now like to go through here. And yeah, it's great that everyone joined me on the stage already for that reason. So I'm gonna post them to the to the respective presenter then. So starting at the bottom here, we have a comment or question from Anissa, who asks, thank you, Diane, for your input on the QPatch Compact. I'm wondering how you would use a system like the QPatch Compact for neuroscience applications. Sorry, I cannot hear you. I'm not sure how that is for others. That's yeah, perfect.
Okay, apologies. Somehow the settings got flipped over. Yeah, so I'm going to take a best guess at neuroscience applications, but I think that Adit and Alice cover this a bit. For single cell patching, fantastic. For cell lines, I mean, obviously the system, if you start to look, requires a fairly large number of cells to be be pipetted in, and they would be dissociated. And so for doing biophysical analyses that we showed, I think it is fantastic. I would say that, I mean, obviously Adit mentioned slice work and other like cultured neurons. Of course, one can't use the QPatch compact system for that. And so for doing circuit analysis, for looking at synaptic transmission, any kind of system where one is interested in cell-cell interaction and/or looking at differentiated cells, then this is not system. But for doing biophysical analysis in spherical cells, and particularly expressing, I've only had experience and very limited experience using cell lines expressing cloned channels. It was fantastic. We also looked at voltage-gated sodium currents. And actually the speed of the clamp was really good. These are fast currents, and so for those applications and what we described, fantastic. Single channel recording, obviously not. And one would do cell attached patch recording, but for what we described within the parameters that we've been using, great. I know that others, and I can't comment on this because we haven't done it, are trying to use the QPatch system for looking at freshly dissociated cells, but I have not had that experience. Hopefully that's helpful.
Yeah, no, that's a great answer. Thanks. And just regarding your last comment, I want to point the audience towards another webinar that we've done with a postdoc from the group of Dr. Waxman, who isolated primary DRG neurons and used the Cube, which is our high throughput technology for such an investigation. But so there are also efforts in that direction. I'm moving on to another question, another one from Anissa here. As someone who took 6 months to learn manual patch clamp during my PhD and a few years to master all the parameters of the amplifier and digitator, etc., a question for Adit. Would you say that you have a good overview of electrophysiology after just 2 days of training on such a small machine where you don't fine-tune anything with buttons? And I see there was also a discussion going on about this topic in the chat. Oh, sorry, Adit, I cannot hear you. See, seems like maybe it was changed for everyone, the settings there. I can't hear you at my end. That sounds good.
Yeah, I think when we came in and out, somehow the setting audio, where the audio is picking up, got switched. And give Adi a second, and if you want, I can jump in and answer it. But go ahead, Adi. Yeah, we're not hearing you. No. Well, let me jump in and just address it, and then Adi, once you've got your audio going, if that's okay, or we can jump to a different question.
No,
but,
I think that would be great, Diane. I mean, if you don't mind, and then let's see if we can.
So I can address that, and then also the discussion around capacitance compensation. I think that look, you can't learn electrophysiology in 2 days, but what I think was really incredibly beneficial from my perspective, and I think also from Alice and Adit and their colleagues' perspectives, was this ability to come up with hypotheses and then test the hypotheses, kind of, as they said, kind of on the fly, building new protocols, asking like, let's look at the recovery, time course of recovery from inactivation, let's look at the tail currents, let's look at extracting PO and the instantaneous current voltage relationship. And this is going to mean something to those of you who are biophysicists. But the focus on that over the 2-day time period, rather than the, training someone to look in a microscope if they've not looked in a microscope, or the manipulation, for me was much more intellectually interesting. And again, like, I think that would make sense to everybody. Could you be an electrophysiologist in 2 days? Or no. Was the focus on the theory and the testing and the observation in real time beneficial? Absolutely, yes. Stability was great. So we were able to do hour-long recordings with no concern, as Adit said, about someone walking in and then jiggling the rig. That was great. So very, very good recordings. Capacity compensation, twiddling the knobs. That I've spent 35 years doing that. But so the value is that there are 8 channels, and so you can either do 8 individual cell patching, or you can look at the average activity of multiple cells in the wells. If you look at the individual cell patches, you can eliminate the ones that aren't well clamped. No, you can't do capacity compensation, but what you can do is to select for those cells where you've got really fast clamp if you really need it in order to be able to get good space clamp. So it's much more, you can do that by numbers if you're really focused and care very much about the time constants and really, really, really high quality space clamp. That's my answer, quick answer. We could get into more detail if you want, but they're my quick answers. I will stop. Don't know if we've got Adi. Is
it working now? Oh,
yes.
Wonderful. No, Diane, you pretty much answered it. All I was going to say, Anissa, is I think the way I split it in my mind is I think there's learning patch clamp, and then there's learning electrophysiology. And I think you're right that, just if you want to learn the intricacies of patch clamp, like how you get a seal on a cell, how getting a seal gets you the data you need, QPatch wouldn't be as helpful. But from the perspective of learning electrophysiology concepts, like how does voltage affect current in certain circumstances and stuff, I think this is a bit superior, only because you're able to get a lot more information and data, and it's a lot easier to change the parameters while you're doing it. So I'd say a few hours on the QPatch versus a few hours on manual patch. I think you'll learn a lot more about ePhys concepts on QPatch just because you'll have access to more data and more experiments that you can run within a few hours.
These are great answers. I mean, I would like to add a few points about this as well, because I completely sort of agree with the points that you made. But one thing that always strikes me so much is that I think there's sort of what we hear often in the industry is that there's a shortage of electrophysiologists. And I think, to me, something like that, where you can generate excitement in a course. I mean, obviously, if someone is a biophysicist really interested in it, that person wouldn't mind sitting down for like weeks and weeks to learn the manual patch clamp technology. But if that's not something that you have a pre-existing interest in, I think such a course as you had it now can really help to spur interest, because you're immediately able to get data. You're able to, in a live experiment, see data coming in, and with a very high likelihood you're going to be successful with that as well. And I think the other thing that probably holds a benefit here is we're going to be able to prepare people also for, especially in the industry, but also increasingly in academia, we see that people are adopting that technology. And I think working with such a platform will also prepare you for these requirements that are out there. Again, it's obviously also, if you really want to learn electrophysiology, you have to sit down. There's no way. You need to learn the details about series resistance compensation and how to do it. But I think that as an intermediate step is probably very valuable. All right, fantastic. I'm going to move on to the next question that came in from David. Thank you, Diane, Edith, and Alice. Was the QPatch Compact system better and easier in achieving stable whole cell recordings in high or medium throughput experiments compared to traditional patch clamp techniques? So I don't know, Alice, you didn't have a question yet. Maybe I can post it to you.
I guess I think I already addressed that. I wonder if Alice could pick up the question about the data analysis. It was much more stable, but yeah.
That sounds good. Yes. What you compare to, yeah, running QPatch. Yeah, so I think we also spoke a little bit about, feeling comfortable running the system after that training. That is a question from Anissa here again. Does anyone want to comment about this? Edith, Alice?
Alice, why don't you maybe jump in and talk about the data?
Yeah, of course.
Perhaps.
Okay. I can answer this question that was just asked, where if Audit and I would be comfortable. I think Audit and I would be comfortable probably running the experiment, but it would be good to have a professor with us, just because on our end, like, we think we maybe understand. We're learning over the course of 2 days. Like, there might be things that, oh shoot, like I accidentally like completely just blew the, like, I put the time course to be way too large, like, or way too small, and I wouldn't necessarily immediately just know that off the top of my head. Some supervision is good, but like, essentially what we did at Neuropracticum is Diane would propose, like, why don't you all study perhaps the, like, try some voltage test pulses, and she would just talk through things with us and we'd be able to do it ourselves.
All right. I think I actually can post the one here. I think, Diane, that's the one you meant about the analysis, right? So here is a question, yeah, for you, Alice. Do you think that you can use your data processing to go back to the experiment setting and find better parameters to evaluate some biophysical parameters?
Yeah, I think we definitely could. Like, even with just looking at the, like, Excel file and looking at the individual sweeps, we could tell, like, okay, maybe like a particular cell isn't super well patched, or like maybe it's not super well clamped, or maybe the cell, like, we were able to see a lot of these things, and we could definitely go back to change a lot of the experiments that we wanted to run. So for example, that first day that Diane, Audit, and I worked together, we ran some analysis. We were like, oh, okay, so it looks like we could try a different set of experiments on the next set of cells. We can try flowing in different solutions, putting in tetrodotoxin, or other things like that.
Excellent. Yeah, I think that makes sense. Alice, since you just unmuted on the stage here, I can probably give you that next question here as well. So there was a question regarding the analyzer software, which is Sophion's proprietary software that we've developed. And the question here from Thea is whether there was a reason for you to use your own scripts, the Python scripts, instead of the Sophion analyzer software. If you could comment on that.
Yeah, with regard to why I use my own things, it was just I wanted to do it in the comfort of my own room, and I didn't have the nice machine sitting with me in my room, so I just wrote what I had at home or when we were in the dorms or having dinner, because otherwise it would have required me to maybe sit with that computer.
All right, yeah, and I think it's probably also a great exercise to go through developing the own project and protocols here. Diane, maybe I can ask that question to you, or Adit, if you want to comment then as well. Does the cell size matter for these experiments?
Yeah, I can comment. Yes, it does. But it isn't solely the cell size. It's the ratio of it's really yes, it matters in terms of the access and the ability to be able to clamp the currents. And so it's a combination of those things. What's the current density? How much current can be passed in order to be able to maintain and how quickly to maintain voltage control. So again, like you will run up against those limitations, whatever method you use. You can't in the QPatch Compact be able to do any compensation. So I think you need to be able to. I mean, what I would typically do in my lab is to reduce the size of the currents by modifying the concentration of the permeant ion and increase the size of the pipette in order to get better space time. But yes, it will. All of those things will matter depending on what you are asking and what components of the current you're trying to measure and how important, whether you're just looking, is the current getting smaller or is it getting bigger? But if you really want to define the biophysical properties, one will need to pay attention to that.
Yeah, and I think maybe I can add here as well. We do offer different hole sizes for these consumables. I think in the course you've been working with our standard hole size, which is sort of a sweet spot between having good series resistance properties and good seal forming properties. But we do also have smaller holes that, for example, can be used to patch smaller either cells like neurons, soma of neurons that are at times much smaller. But also we've seen some studies being done with even with mytoblasts that of course are much smaller, and they can be used for that. I think Diane, you already answered the question regarding the slice recording. This is not possible on the system here, so it is a single cell technology. But maybe Michael, I can give you that last question that we have here from Bhavya. Hello, how would QPatch system work for ligand-gated ion channels?
Yes, can you hear me?
Yes.
Good. Yeah. So in the setup software and the data acquisition software, the user sets up whether it's a voltage-gated ion channel or a ligand-gated. So there's a specific setting for that, and works very well as well for ligand-gated ion channels.
Excellent. Yeah. I think that microfluidic flow channel that the system features really allows to completely exchange the solution there, which can be a very helpful tool. I actually noticed I did jump over one of the questions here from Sarah. Great presentation, everyone. How did you manage to supply of cells for the experiments, and how many cells perhaps did you have to do per day to keep the experiments running? Adit, do you mind answering or addressing this?
Hello, can you hear me?
Yes.
Okay, good. I actually think this might be a better answered by Diane. I forget a little bit about the cell prep at this point.
Yeah, just very quickly, we used two different cell lines. One generated in my lab that expresses voltage-gated calcium currents. So these are the large T antigen transformed HEK293 cells, so human embryonic kidney cells, and they have a high level of expression of the clones that we clone in my lab. And then we also use some cell lines expressing voltage-gated sodium currents. I think now 1.7, but I'm not really remembering. But they both work great. And in fact, during the course, one of the technicians came and tweaked a few of the settings, and we were getting incredibly regular, really good seals and really good recordings. So they were the cells. In terms of like how many, well, they're cultured cells, so we're just harvesting them constantly, and you need enough high enough density in order to be able to obviously fill the wells each time. but I couldn't tell you what the cell count is, but I bet that if you contacted the folks there, they'd give you a good estimate of cell density that is kind of optimal. Yeah.
Yeah, great. And yeah, so I think like our recommendation typically is between 5 to 8 million. We just see a relationship like with higher concentrations. The seal is it's a stochastic process that if the higher the concentration, the higher the likelihood for the first thing to hit that patch hole to be a cell. That's why we use these relatively high concentrations. But I think with the QPatch Compact, using 5 microliters per well, you can still keep the absolute amount of cells relatively low. I think this one we have answered already, this question. There's just one last minute question that came in, I think, before we close it. How can you learn about these softwares, like how to analyze? Alice, do you want to comment on this question?
Sure. I'm not sure if this is referring to the Sophion analyzer software. In terms of like MATLAB and Python, I had just taken some courses on it in the past, and I just like Googled it, or I would just ask the internet, like, oh, can you fix my syntax? And it'd be resolved by that. But in terms of how to learn how to use, say, like ClampX or the Sophion analyzer software, I think there's probably instruction manuals online, and I'm sure like for Sophion, a software rep would be happy to help you.
That's exactly right. That's the part that I would otherwise have added here at the end. The other questions that popped up, I think we did answer all of them. And regarding the question, also how should be the thickness, I would assume that this is more addressed towards the sliced recording. And we've answered that this unfortunately is not a possibility with the system. I think at this point, I want to thank everyone again for providing that feedback. That was very, very interesting to me. Thank you for your presentations. And yeah, so with that, I have just a few remarks at the end here. I also want to thank, of course, the audience for joining us today for this webinar, everyone who sees it at a later point. I do also want to thank my colleague, Jette Juhl, who is arranging all of this in the background. And she's really been instrumental in bringing that to life here. Again, if you do want to learn more about the QPatch Compact technology or any of our technology, you can find information at our webpage, www.sophion.com. And yeah, there we have videos, as I mentioned. There will be a recording available of this particular webinar, and we'll send out links after this. And then last but not least, there are lots of interesting and exciting things happening at Sophion Bioscience. And I do ask that if you're interested in a technology, please stay tuned, because in a few weeks, we will have some exciting news coming out about the QPatch Compact. And these will be posted either at our webpage, but also LinkedIn is a very good source for following all the information that we are posting. So the Sophion LinkedIn page, if you follow that, you'll get all the updates on your feed. So last but not least, we do have a number of Sophion hosted events coming up. And first and foremost here is our user group meeting in the United States that we hold at Harvard University, and in conjunction with the lab of Professor Bruce Bean. And that'll be here in August 24th and 25th. And we already have some quite exciting lineup here. So if you're interested, please, on our webpage, you can sign up for that event. We also have a user group meeting coming up in Europe. That'll be in September 7th and 8th in Copenhagen in our headquarters. And then we also have this yearly, the annual meeting, the Ion Channel Modulation Symposium, which is an academic, mostly academic event where we really have ion channel focused presentations from all areas, from all disease states, and from all from structural into really functional studies. And it really casts a wide net over what is happening in the industry and in the field. And so for the third time, we have this meeting in the US, and that will be in at the University of California in Irvine here at on October 18 and 19th. I think we are quite excited because we've secured Professor Adam Pataputian as the keynote speaker for this, but we have other exciting presentations from the industry and from academia presenting as well. So once again, thank you for joining. Thank you to the presenters, and we're looking forward to hearing from you. Goodbye.